What if the solution to our energy future isn't just using more renewable sources, but reimagining how we use them right now?
Wind surrounds us, clean, abundant and free, but traditional wind turbines don't capture its full potential.
That's why we created Halogen, a turbine that doesn't just use wind energy, it reinvents the blade itself. With spiral form, it extracts more energy, especially during low wind conditions.
Our project is aimed to support Sustainable Development Goal number 7, affordable and clean energy, specifically Target 7.2.
Globally, wind energy accounted for only 7.8% of total electricity generation in 2023, despite its rapid growth and potential. Even in countries with strong wind deployment, modern turbines typically operate at only 45 to 50% efficiency, which is relatively far from the best limit of 59.3%. This shows room for future improvements. Wind energy has a strong potential, as Denmark led globally by generating 59% from wind in 2024, showing possible results of relying on turbines. However, current turbines struggle in low wind or urban settings, limiting adoption, scalability, and even economic viability of clean energy in many regions worldwide, as even countries like US could only reach the value of 12%.
Halogen uses spiral blades, which are more efficient alternative to traditional airfoil blades. And this change is grounded due to aerodynamics and fluid mechanics. So according to Professor Desmond Adair, the blade's spiral shape changes wind's direction as it passes through the spiral blade surface. And as you know, velocity consists of both magnitude and direction, and change in either of these components results in acceleration. So as airflow passes down this blade surface, it accelerates. And according to Bernoulli's equation, this acceleration results in static air pressure difference between the sides of the blade, and this enhances the lift force acting on the blade even more, which generates more efficiency. And also, Michael Zhao further supports this through the Magnus effect, where spinning air flows around the blade enhance lift force even more as airflow gains angular velocity due to, again, changing the direction. And we tested this theory by crafting paper and wooden prototypes followed by 3D printed models, and our experiment confirmed increase in electromotive force that was measured using multimeters and improved power generation at both high and low wind speeds. And the results were drastically higher at lower wind speed, which proves efficiency of our blades in these wind conditions.
To take our prototype into the real world, we've constructed a step-by-step strategy. 2025, applied research using computational fluid dynamics and measuring real-world performance. 2026, testing of 3D printed full-scale blades in high wind corridors. We'll also build partnerships with government ministries, grant agencies and companies. 2027, certification of process and our first commercial sales. 2028, regional expansion across 2 to 3 neighboring countries. 2029, pilot programs in cities and integration of our turbines into microgrids. And by 2030, our goal is to have over 5,000 working units generating more than 30,000 gigawatt hours of clean energy every year.
To deploy our full-scale spiral blade turbines, we will have 5 categories of resources. First is human resources, that involves electrical and mechanical engineers for turbine design. Second is land and facilities for wind turbine placement. Third is materials and hardware. The blades will require fiberglass, epoxy resin and chroma for larger turbines, and small-sized turbines in urban areas will be made of PLA. Fourth is partnerships and agreements, for example with government and city administrations. Fifth is data infrastructure and software, such as cloud-hosted IoT platforms for real-time maintenance and alerting.
Now coming to the pricing, we estimate that the cost of the spiral blades are going to be 29% higher than the traditional ones due to higher volume and surface area. So it's going to be like 105,000 USD versus 81,000 USD. But in terms of the whole turbine, it's going to be only like 6% increase in price. And considering that our efficiency matches the price cost increase and that will have a lower wind threshold, we believe that the payback period will be in fact shorter, or at the worst case it's going to be the same. We're aiming to fund the project through partnership with manufacturers as well as international environmental competition with prize monies, and lastly it's going to be like Kazakhstan's national green energy support associations. We made a detailed business plan that you can see right now on the screen. You're free to pause and just look at different stakeholders and etc. and our revenue streams.
HelixGen is designed for long-term impact. Its modular 3D printed plates allow for easy upgrades and part replacements, reducing costs over time. Due to lower pressure on the blades, we can use thermoplastics like PET or HDPE. We support a circular economy, and therefore we try to cut waste. Unlike traditional turbines, HelixGen works in low wind regions, expanding its market relevance and deployment lifespan. This flexibility ensures it can adapt to changing energy demands, making it a viable solution for both current and future green infrastructure.
In our experiments, spiral blades generated up to 300% more electromotive force in the low winds and 30% more in the high winds than traditional blades. We identified an optimal twist angle of 20 to 25 degrees and determined that blades perform best when wind flows parallel to the axis. Our CFD analysis confirmed higher thrust in all cases, and SWOT analysis showed trends in efficiencies and low noise design. We plan to install HelixGen in urban environments powering IoT sensors, lighting, and EV stations. So now, let's talk about the benefits to society. If scaled, HelixGen can, first, help meet growing global energy demand. Second, reduce CO2 emissions. Third, enable decentralized energy in both cities and rural areas. Fourth, create jobs in green tech and 3D manufacturing. And finally, fifth, integrate with smart city and IoT infrastructure. So in short, it's a leap toward independent, renewable, and sustainable future.
Thank you for watching. Let's make wind energy efficient, accessible, and urban. Scan our QR code to view live experiments and CFD simulations. Join us in shaping the spiral energy of tomorrow with HelixGen.